very much for coming, and thanks to the other organizers for having this wonderful week. So I want to talk a little bit about thermalization of quantum memories, and what I want to do is show some. I want to show some results that so the reference for this of archive is this paper. Which is together with David and Antonio Perez Hernandez in Madrid. But I will try to take a very kind of pedagogic approach, so I will not really talk about the most general case we covered, which is the case of quantum double models introduced by Kitaev. I will mostly talk about the Turing code, which is a model we all, I mean, maybe not all, but I'm sure many people have heard of the Turing code. And it will allow me to kind of actually give a little bit of a feeling of how the proof works and explain the techniques. But this result for Turing code is not new, so I'm going to show kind of an easy case. And the difference in our approach is that we actually use Tensor Networks. Maybe this is more interesting from a technological point of view of introducing some tools. So let me just kind of do, set up the notation and remind a little bit about the Turing code. So we are on a discrete torus, n by n, and usually we put qubits on the vertices of a graph, but for a Turing code it's a bit nicer if you put them on the edge of each qubit here, and we have this picture. Here you have two-dimensional. So I want to introduce a local Hamiltonian, which has commuting interaction, and go quickly because this is not particularly new. On vertices, I have some interaction terms, and on brackets, I have some other interaction terms. These are defined in terms of commuting, and that's defined in terms of Pauli operator. So the stars is the tensor product of 4 Pauli x and the packets are a tensor product of Pauli z. And you can check that this is in commute because basically Pauli x and Pauli z anti-commute. So when they overlap, you have two terms which anti-commute, each gives a -1 contribution, and the result is that and so what happens to this model is that you have a general ground state subspace dimension 4, and so you want to think of that as a space where you want to encode some state. So this is somehow the model of quantum memory. So we have ground states. It's 4-dimensional. And
can I just ask, so for the finite system, what do you do at the boundary? You just include all those terms with...
We are, sorry, on a torus.
Oh, torus, sorry.
So there is no boundary. And you can do things with the boundary for a planar model, but it's easier to work on torus. And so what happens is that you have this 4-dimensional ground state, and people call this topological model, and the reason is that there are, if you want to basically transform one ground state to another, you have to do something which is macroscopic. The idea is that, for example, if you act locally with a Pauli operator on a single edge. For example, if you take a ground state and you apply a single Pauli X here on a single edge, the net effect is that this Schuh-Plaquette operator now will not commute with the operation and will give you kind of a little bit of energy there, which you can somehow detect locally, right? So the idea is that here you have some particles which have been created by this operation. And now if you keep acting with this, with other sigma x's on the kind of nearby, what happens is that you're moving this, this excitation one side to the next. So you're creating this kind of process with a string of sigma x's, moving your anion around. And then at some point you're on a torus, so you wrap around, you end up in a situation where you basically now have a loop of operators wrapping around your torus. And when you do that, this is some sigma x tensor n. When you do that, these two excitation fuse back together, and what implement is some unitary operation of a ground state. And depending on which ground state you're starting from, this might end and give you an orthogonal ground state. So somehow logical errors in the code can be created by macroscopic operations. And so the idea of this is that if you have a noise process which is doing, maybe not this, but some process which is creating excitation, maybe because of this fact that these operations need to be macroscopic before you can actually implement a logical error, so the expectation is that it might take some time to do this, right? Because he has to actually generate enough of these local operators to actually create this local. And so you can think of the thermal process. This was a classical model. You could think of this as like a random walk or some sort of walk of this excitation. And then, of course, this is a quantum model, so it's not so clear. But what I want to do is try to argue that we can study this kind of thermal process of this kind of excitations and try to understand what happens in this model and in a larger class of models. So I want to introduce temperature, and I want to think of that my toric code is in a contact with some thermal bath at inverse temperature beta, and I want to study the resulting dynamics and try to understand how quickly this thermal process can reach to equilibrium. Analyze the behavior of these models under effective load. And so there are like many ways you could answer this question, and I don't want to go into too much details, but there is one which I believe is mathematically more justified than others, which is called this so-called recoupling limit. And the result is by Davis, also known as Davis generators. I think it's 1976 or 74. Yeah. Around 1976. And so the idea is you take a thermal bath at finite temperature, a positive temperature, and you look at some coupling between your toric code and the bath. So the coupling will look like your toric code Hamiltonian, some internal Hamiltonian of a bath, plus some coupling term with a parameter lambda. So this is some sort of expansion of the coupling terms in terms of like local basis of operators. And so the evolution you would like to look at is the unitary evolution generated by this h lambda, but we don't really care about the but much. We really care what happens on our system. And so what you do is you look at the reduced effective evolution, you do a limit to get a more easy to work with theory. So what with coupling limit is the limit when lambda goes to 0. So that's why it's called weak coupling. But you keep this parameter lambda squared t constant. So somehow you rescale the time parameter by the coupling. Because this is constant, this is going to 0 t.
The letter on the left.
Oh, should be a tau.
Oh, that's fine. That's all.
Question, what is the operator of the system that couples in the lambda term? Is it S alpha? What is that?
Yeah, so this is some, I haven't really specified, is a set of operators which are the effect of a but on your system. And I will have to say something about that in a minute. But just think of this as some sort of tensor expansion of the coupling terms in terms of some operator.
And the toric code has some excitation gap, right? So is there a relationship between beta and the excitation gap?
Right, so the
Bigger,
toric code
smaller?
is commuting, so the excitation gap is always 1,
Right.
or the parameter you can put.
Right.
It won't really, it's not, because it's not the gap I want to look at in a sense. This is, maybe it is related, but it's not what I'm. And so what happens is, there are a set of assumptions you can put on the but, and I don't want to get too much into the technical details, but there is a way of making this limit of this evolution rigorous and obtain what is a reduced evolution on the toric code alone, which is something of this form. So if you have x, which is some bounded operator on our Hilbert space of the toric code, the time evolution under this reduced evolution is just given by a generator L. And L is composed of 2 terms. One is somehow a derivation by the toric code Hamiltonian, and a term which is a dissipation. So let me just explain what it is happening here. So delta ht is the standard commutant. So this term here will generate a Heisenberg evolution if it was on its own, and this guy here is the dissipation. So
This is in the spirit of plain Lindblad.
Yes, exactly. So this is a Lindblad, or K S L Lindblad. I call it Lindblad once in a talk, and some people complain that it was Koski. So this dissipation is somehow responsible for making this evolution not unital, and it's actually going to be a semigroup of unitally positive which converges to the thermal states. So this dissipation has a specific form, which depends on the S alpha there you define. So this is you have still some edge decomposition of this derivation. Derivation is dissipative term, and each of these is some sum over the alpha and some values omega of something which looks like a Limblad term. Well, it is a Limblad term. Now omega is running over the spectrum of delta HT. So these are differences in energies in the Hamiltonian, and each of these S alpha omega is responsible for making an energy jump between some energy E and energy E plus or plus omega. Right? Omega could be positive or negative. So this is differences of energy levels of the spectrum of the Toric. So this is actually my starting point. So this is the object I want to study, is how does this process behave on this model? How quickly this process will reach a thermal equilibrium. So this is now contraction semi-group, and so at some point it will converge to the thermal equilibrium. And so one thing is interesting of this construction, which is not obvious at all. I'm just kind of summarizing a little bit this result by Davis, is that these two terms are actually commuting. The unitary part, or the generator of the unitary part of evolution, and the generator of the dissipation are commuting. You can check this. And so if I look at the spectrum of this object, because these are commuting terms, I can kind of just look at the spectrum of the two terms individually and sum them together. The unitary part has a spectrum which is...
Is that a condition on the S, or what?
No, this is an effect of the way this limit works. Kind of comes up of taking this limit.
But this will not hold generally, not take a general Hamiltonian, a general D, or a general set of S. So that's a specific set of S which we have here.
Maybe? No. Maybe. I don't think this happens for any choice of jump operator.
Really? That's suspicious.
Because this S omega, S alpha omega are like the full frequencies of this. Right? And so I think it should. I see people, some people are nodding, some people are shaking I'm saying it's not true. So let's take this as maybe as an assumption, and maybe condition apply. And so what happens is that this, if I look at the complex plane, the spectrum of this unitary generator has to live on the boundary of the unitary circle, because it's a generator of a unitary evolution. And then the spectrum of the dissipative part is also contained in the disk. And what happens is that basically most of it will be in a smaller disk, except from a fixed point, which is 1, and this is what people call the gap. It's like the difference between the largest eigenvalue. Sorry, I should have done this is
the spectrum of what?
This is the spectrum. Yes, sorry, I should have done this differently. This is the spectrum of e to the I delta HT and e to the I L T in some fixed. So you should have done the
There's no I from L, right?
should have done the other picture. Apologize. So the spectrum of I delta T is on the imaginary line. This is the spectrum of then the spectrum of the dissipative part has a kernel, and then everything else is on this left-hand side. This hyperplane, and this is the gap now.
That's what you call the vector.
Yeah, so that's not it. This is E minus E gap. Right, so as time increases, what happens is that the subspace of corresponding to this part of the spectrum will go to 0, and I will only be left with this fixed point plus, of course, the unitary evolution. So what I want to study is exactly how big this gap is, because it's telling me how strong the dissipative effect is, how quickly this thing will destroy information in the model and converge to fixed point plus this unitary evolution. So I want to forget about the unitary part, because it's really not the important thing in this analysis. And I want to focus on the dissipation. And so the punchline that what we could prove using the methods I wanted to show is that this, if I make some kind of minor assumption or like reasonable assumption of this S alphas, then this gap is lower bounded by a constant independent of. So this is the theorem. And let's say assume, for example, that the S alphas are a set which generates, which do not have any trivial operation which commutes with them, then this gap is larger than some constant times an exponential decay in temperature and some number lambda toric code independent of system size. Which means it doesn't matter how big your system is, this idea that macroscopic observables should be harder to generate is not reflected in the gap. So this process has a kind of time scale convergence to a fixed point, which is completely independent on how big your torus is. Which kind of makes this memory not a big.
So where is beta in your model?
In the fact that this.
No, you had
Right, yeah, you're right. I should have said the G alpha omega depend on beta. But the S alpha omega do not. So these constants are the ones where the beta temperature is.
Is there a specific form of the relation between G and beta? Because you have a very specific relation function of beta there.
Because they have this decay balance here. G of minus omega is e to the minus beta. G of omega is like the probability of doing transition from a certain energy to energy plus omega. And this detailed balance is basically saying that the ratio between going up and going down is exactly the Gibbs weight at temperature beta.
So obviously G is dependent on beta.
Yes.
You said so.
Yeah.
And the rotation is.
Yes, I should have. It should be a beta dependence on omega.
Why did you specify this E dependence? I don't see any E's anywhere. You write the D
Right,
into
because
some
what so I should have added here that the coupling terms are done locally. So each single edge has some thermal bath, and all of these thermal baths are independent from each other. So this is a particular assumption on the noise, that somehow there is no correlated noise across the system, of course, if you could act on the system as a block, then you could do more things. And I'm kind of restricting to a simpler model, but also more restrictive. Each noise process somehow is only acting on each edge individually.
Excuse me. So what is the assumption again? What you make on the S alpha?
Well, that they don't, they do not have any operator which agree with all of them. There's no operator. So this forces the resulting dissipation to be ergodic, meaning there is only one point here in this fixed point, and then everything else goes to zero. So which guarantees that it's actually converging to the thermal state. Of course, you could have three, like, bigger model where there is no.
The actions are purely local.
Yes. So now what I'm assuming here is that each S alpha E is acting on a single edge.
So what about if you have something like a wave passing through the system, which has a momentum to it, which is kind of global in a certain way? Not S of X, but S of K?
This doesn't cover it, I guess, but I also, I think the intuition is that should make it easier to break the memory, right? Because then you can create larger errors and move it faster. And this result says even single side noise is actually pretty good at thermalizing very well. It doesn't scale with N, which means it doesn't matter how big this system is, the kind of the relaxation time is this one. Yes,
Can you say more about like what the structure of the S alpha omegas are in such a way that, like, for example, it's definitely not obvious that it commutes with the Heisenberg portion of the evolution. But like, is there a particular structure or intuition why it's written that way?
each of them individually they don't, but collectively, yeah.
Are you sure this Hamiltonian is the original Toricode Hamiltonian?
Yes. I mean, these S alpha are defined by taking the Fourier components of the S alpha omega are defined by the Fourier components of this Heisenberg, the free kind of unperturbed Heisenberg evolution. So these omegas are exactly the only numbers you need to write this down. And so basically what this S alpha omega does is exactly map a certain energy subspace to a different energy subspace. So they are not Hermitian, and going down in energy is the opposite of going up. And I agree. I think the commutation with the unitary part is not obvious, but to be honest, I really don't want to spend too much time on that. Because if it's not true, I mean, I'm just talking about the gap of the dissipative part, and then we can argue whether that's an interesting question or not. And I'm relatively sure. This result, so for the Tori code, this was known since 2009, and this was done by Leakey, Farnes. I apologize to the Polish people in the audience. I don't pronounce Polish names. And a similar result was obtained for 1 billion quantum doubles, which I haven't defined, but the Tori code is the Z2 case, and so instead of Z2 we have an 1 billion group, and this was done by Kumar, London Cardinal. and by Christian Demmer in 2016. And then our result from 21 covers all the other finite groups. So this is the non-abelian. So the new is the non-abelian. But on a more technical point of view, we prove this using a tensor network representation of this thermal state, which I want to use the Tori code to kind of try to explain it. And then if you're interested, you can look at that paper to see how this is generalized. But I think it's interesting to see this problem from a point of view of tensor network. So let me give you a very, very brief overview on what happens in the proof. And I hope it will kind of explain why I'm not giving too many details on these Davis maps, because they are actually not that central until the very end. But of course they are. So the steps, somehow, this kind of the overview is the following. We look at the deep state of the Tori code, the temperature beta, which is this guy. This is the density matrix of the Tori code. And it's somehow a reasonably known fact that this can be written as a paper, so as a projected entangled pair operator, so as a tensor network. And then what we do is we do a local purification of this paper and we obtain a PEPS. So we look at what is known as, because you can also write the paper for rho 1/2, you can purify rho 1/2 and you get what is known as the thermofield double, which is this state here. See, tensor identity acting on some maximally entangled state. It's kind of a local purification. If you trace out half of it, you get back your. And this is a PEPS. And so, because that's a paper, this is a PEPS. And so now we just start applying the PEPS machinery. And so what we do is we construct a parent Hamiltonian for this state, and we show that it has a spectral gap. We call it H parent. And this is now a non-commutative interaction in Hamiltonian, and this lives on a two copies of the Hilbert space. We have purified, and we show that this is gap. And this gap has nothing to do with the gap of the original Tori code Hamiltonian, which is 1. This parent Hamiltonian will depend on beta. And then up to here, it's like this has nothing to do with the Davis, but in the paper of Aliki, Fanel, and Loreski, what they did was use this detail balance condition to also write kind of a purification of the Davis generator acting on this double hyperspace. And so we can purify D and kind of convert it, or actually we can purify minus D, so we have a positive operator, and obtain a different Hamiltonian. We have an Hamiltonian which is not the parent one. But the ground state of this purified dissipation is still the thermofield double, this purified Gibbs state. And so now we have two local Hamiltonians acting on the same space, and they have the same ground state. And so we want to compare them. And so you try to bound basically the interaction of one with the interaction of the others, and you work a little bit, and you show that the gap of this purified Davis is still the gap of your original generator, and this is bounded by the gap of this parent Hamiltonian with some constants, which are the ones we get in our theorem.
Question.
Yeah.
D is a linear operator in the space of, is a linear super operator in the space of like operators.
Yeah.
Or like, I guess it's dual is like linear in density matrices.
This is the Heisenberg picture, so it's really acting on operators.
But then once you take the square root in the purification
Yeah.
picture, D, I didn't think D was a super operator in the square root of rho. I thought it's linear in rho.
It's linear in rho, but it's not. I mean, this D is a linear operator, right?
Acting in the space of density matrices or operators, I thought.
Right.
But in the purification, is it still linear?
Sure. Because it's. I mean, I'm just writing. I'm just kind of introducing a scalar product on B of H and making it to a Hilbert space. It's like a different presentation, if you want, of the same object. It's just that it lives now in the same kind of space where this parent Hamiltonian lives, and so I can more directly compare them. There is a, it's like a unitary equivalent. Maybe I don't understand your
I'll
question.
ask the question later again.
And so this part here is actually not, not maybe the most interesting one, at least from a tensor network point of view. This is where all the kind of tensor network business happens. This is just comparing two different. So what I was hoping was to focus on showing that this object has a gapped parent Hamiltonian.
How specific is the statement in 4 to the, like, what properties do you use basically to show that the gap of the dissipation D is equal to the gap of this parent?
So we need this ergodicity condition also to guarantee that the ground state is unique. Otherwise, this would have multiple ground state and already there. And it's not really specific to like it. What we assume is basically the structure within the generator, and this the tail balance and all these conditions. And I think it's fairly well. Sorry, we need to assume something about. So when you purify, you will lose a little bit of locality, and the amount of locality you lose is depending on the structure of the toric code of a plaquette. So you blow up the interaction length, so this becomes slightly larger. But all of these are like kind of work the same for these quantum double models, and I'm assuming that other commuting Hamiltonian models not using much about the specific from the
It's kind of a generalization of the statement that the gap of the global dynamics is the same as the gap of the Hamiltonian construction.
So what is tricky, but actually defining the parent Hamiltonian is not completely trivial. So this object, first of all, is not is frustration free, but is not made of projections. So you have like part of its bound comes from the fact that the individual local terms have a small gap. So you have to kind of blow up the gap to get something constant. But then the parent Hamiltonian is where the structure of this model really influences. And so if you want to compare it, my first question would be how, I don't know exactly what would be the right.
So the parent Hamiltonian depends on D. It's not just a canonical parent Hamiltonian, but a specific one which has some information about D.
It really depends on the paper, right?
But it doesn't depend on D.
No, it doesn't depend on D. But what I'm just saying is that even just part of the issue is like understanding the interaction length, for example, of this parent Hamiltonian. And so here in this comparison, this D has kind of a enlarged but still finite interaction length, this finite Hamiltonian one we feel has a very big interaction length. So already comparing them requires, like, part of this price you pay is due to that. If you want to make a general statement, again, you probably can, but you have to kind of assume something about what the parent Hamiltonian will look like.
Trivial question. One can scale the parent Hamiltonian by an arbitrary scale factor. So what's the unit of energy of the parent Hamiltonian?
Oh, good question. So the parent Hamiltonian, I'm going to build it out of local projections. And so each individual term has like energy either 0, 1. And then I have to fix the interaction scale, the interaction length, and that more or less fixes the energy scale.
The Pipple, I mean, it's not an exact thing, right? So you have to make some sort of an approximation.
Sorry, what?
Turning this thermal state into a Pipple, that's, or can you do this exactly?
Yes, because this is a commuting to the Hamiltonian. So this is some kind of partition. So this is exactly a Pipple.
Okay, but
it's not approximated by. So before I get into why this is available and how to write this expression, I just want to make kind of a brief comment on what we need to have in order to prove existence and gap of a quantum. And again, there are a lot of like previous results that we are building upon, which I don't have the time to get into. But the problem usually is that you want to estimate bounds on expression of this form, where EA is the projection on the subspace of, let's say, PEPS of your specific model in a region A. So let me make this more precise. I'm thinking of a tensor network now, for example, in a square lattice. It's a region A. What you can do is you can tile it with your PEPS tensor, and you can contract all the virtual indices. And this gives you something living on the physical space, except that you have all these like boundary sites still open and uncontracted. So there's not one possible state you can obtain of this. There is like a subspace. Like if you fix the choice of a boundary, you get a physical state. So this defines a linear map from what they call this boundary hyperspace, is the collection of the virtual indices I have not contracted, and my physical space. But here I'm assuming this tensor network is translation invariant, so you fix one small t tensor, and you can define these maps for any choice of your region A. And so when I mean this, I mean the image. PA is the image, the projection of the image of PA. So it's just a subspace of things you can build with. In our parent Hamiltonian model, we would like a parent Hamiltonian to select this as ground states. So parent Hamiltonian is basically, almost by definition, is a local Hamiltonian where the ground states, when you restrict to some region A, are exactly the states you can build with BA, up to taking A sufficiently large, right, avoiding the small cases, right? And so this quantity is basically, for the parent Hamiltonian, is telling you how big the overlap is between nearby ground state subspaces, and somehow it's telling you how delocalized excitation we can be.
Okay, so first, A and B are two different physical regions, touching maybe or not touching?
Well, if they're not touching, these two commute and this is 0. And if they touch, now you have a kind of a problem.
Second, when you say ground state, you restrict to A, I'm thinking of a density matrix living on A.
No, right. What I wanted to say is you look at the kernel. So if my local Hamiltonian is a sum of local interaction, I'm looking at the kernel of only the ones which are inside A.
Okay.
So it's like the open boundary condition kind of local.
And that's an equality and not like include subset.
Yes, I want that to be exactly equal. Which maybe is a, so part of the problem is finding one which is exactly equal, which is why maybe this is harder than it should be. And so what I want to say is that these quantities can be calculated with the tensor network representation of VAs. And the idea is the following. You define a boundary state, which is a density, not normalized, so a positive operator on the boundary. So this mathematical notation is just a way of saying you take this region of tensor networks, you take another copy, and you contract all the physical indices. This is what this VA does. You take, here shown for a single tensor network, so a single tensor. When you contract the physical indices, you're only left with the virtual ones, and you can interpret it as an operator which goes from one copy of your hyperspace to the same. This is something of boundary state. And this has something to do with PA because it's kind of easy to check that basically this is the thing which is distorting the scalar product between the boundary and the physical space. So in particular, you can check quite easily that PA is given by PA rho boundary -1 VA. So this is somehow an object which is kind of encoding some information about PA. It's not so surprising that we can estimate these kind of bounds using these PAs. And so the result is, write it properly.
There's a stick.
I can stay there for
The hook.
This one is a hook.
The other end. The other end. But you don't need it now, right?
I'll take it down later when I need it. So this was done in a previous paper with Michael Castroiano, who was also here. Basically, what we did was saying, if you can find a good approximation to rho, which is local in a sense, which one has to specify, but for the sake of today, let's just say you can find an approximation rho, which is a tensor product. Make it a bit easier to state. So let sigma A be another density, or like another positive operator on the boundary, which is the tensor product over the boundary site.
Question.
Yeah.
Does it matter whether the tensor network's injective or not, or
It doesn't matter. So if it's injective, rho will be full rank. And if it's not injective, rho will have a kernel, which is exactly what is missing, right, for injectivity. But if you look at the formula, the inversion of rho is only happening on V. So somehow you can think of that inverse as a pseudo-Mersenne on its kernel, like on the complement of the kernel. And anyway, PA will be 0 in that case. So I'm just doing this in abuse of notation and use pseudo-Mersenne here. And so here, in fact, if rho A is not full rank, you probably want to find a sigma A which has the same support. Otherwise, the condition will is probably impossible to satisfy. Or you can satisfy, but it's not going to help. And so we look at this. How good is sigma as an approximation of rho? And there are many ways you can look at this approximation, but this is the one we need, which is kind of a weird. So you look at the inverse of sigma and you multiply by rho, and you see how close they are to the identity. But because these are potentially non-commuting operators, you do this kind of balance product instead. And then you say, okay, let's take some region, for example, like this.
Sorry, this tensor product is over individual spins on the boundary?
Yeah.
That's some partitioning?
I mean, it's easier if we just do absolute complete product.
The thing that's, for most cases, you will not be able to get good approximations by products, no? It does not exist.
It's possible, but it is possible for the toric quant. And so that's why I'm kind of doing the simplified version.
Sounds like you're proving a theorem which might not apply to anything, basically.
It applies to the case winning. So that's good. And so you look at some like rectangular region and you split it into smaller rectangles with some overlap, and you look at somehow the maximum between all the approximations you can look at. A, B, the union, the intersection. And so the idea is that if this number is small, then that projection, difference of projections should be small. And in fact, A, B minus B, A union B, this can be controlled by something which, let's say, is 6 epsilon if epsilon is smaller than a third. And if not, you have
6 or sigma?
It's 6. Assuming epsilon is smaller than 1/3, you can find this approximation. If epsilon is larger, the formula looks a bit different. So how can you kind of, if you want to have kind of a sanity check of this condition, you could ask, what happens if epsilon is 0? Like, what if rho is exactly a product? Then this theorem is saying that this projection should be commuting, and in fact, this is something which is reasonably easy to see from the tensor network representations, that it follows that projections are commuting. So this theorem is trying to quantify if you're like this far from being a product, you're this far from being commuting. So I would like to go into more details, but so the aim of the game is kind of to calculate the boundary state for this PEPO and try to find a good product approximation. So this is how we obtain this point number 3. And so let's do this example now of the PEPO of the Tory code. And I hope all of this gets a bit more clear. And I'm going to kind of simplify even more. I'm just going to do the PEPO for the plaquette part of the Tory code. And just ignore the other term. They are commuting, so you can kind of see that these can be made to work in the case. So I want to write e to the minus beta halves the sum over the plaquettes, now it's a plus, as a PEPO. And so first of all, these plaquettes are commuting, so obviously this can be written as a product of e to the beta halves pp, and the order doesn't matter because this is a commuting thing. And now this is a +1 -1 evaluated operator, so the spectrum is just +1 -1, so I can do the usual trick and write this in terms of the product of cosine, hyperbolic cosine of beta halves of the identity plus the hyperbolic sine of beta halves times bp. Just an easy trick. And so, because all of these PEPO and PEPS are kind of, normalization doesn't really matter. You can see also here in this condition that constants will get destroyed. I can kind of, for example, factor out the cosine, hyperbolic cosine, and just write this as identity plus the hyperbolic tangent of beta halves. Just to keep one constant. So now, each of these things inside this parenthesis is a PEPO. So it's a small tensor. So the idea is you want to have a tensor acting on your let's say on a single edge, and then you want to have some virtual bonds here, which I will need to contract to get my PEPO. And so what I want to do is this is going to be the identity tensor, for example, a fixed one-dimensional state, like a projection onto 0, 0. And then it's plus BP tensor. And then I have to add the weight, and so let me put it here, times hyperbolic tangent. So that expression is essentially already, it's like trying to do a tensor decomposition of this. And so now you can see that if you take 4 copies of this 140. I get the constants right. And oh, sorry, I'm getting ahead of myself. This is not BP, sorry, this is a single side Z. Now what I claim is that this object, if you contract it along a plaquette, you get exactly the Gibbs state of a single plaquette there. So now you do with a plaquette, you do this kind of 3D picture, 4 copies of this object, and you contract the virtual lines. Now what happens along the orange line is that either you select the old 0 subspace or the projection to the 1, because they are orthogonal, and so basically this gives you either you get an identity or you get a hyperbolic tangent of beta halves times 4 copies of Z, which was exactly our BP. So this is a single. So you can. I also want to kind of forget a little bit, like separate this weight, because you can see this is just kind of a constant which doesn't really change too much the structure. So if I redefine this tensor to have it without the weight, and then I just add a weight on my pepo. For example, I can put a single dot here, which is 0, 0 plus hyperbolic tangent of beta halves 1. This weight commutes with everything. I could put it anywhere I wanted and just keep it.
Hello?
Yeah.
So we are supposing that these, say, auxiliary dimension of the pepo, they are acting, if I look at the toric code, say, diagonally between edges, right?
Yes, in this case.
Otherwise, they don't
Yes.
contract the right way.
Yes. And so the state I want to represent is the one up there, which is basically the product of all these kind of disks on each plaquette. And so now if I look at a single edge, I have 2 plaquettes which are interacting on that edge, and I should take the product of the 2 in order to obtain my Gibbs state. So the Gibbs state is like a combination of these things. So now what I want to do is kind of isolate a single edge to obtain the pepo tensor of an edge in such a way that after I recombine all of them, I get back to the big product, which is the Gibbs state. So I want to isolate this stuff. And I should put the weight here. And so let me just do the calculation without the weights, and then we can see what happens with the weights, because again, the weights are not particularly complicated. So this is somehow the situation. I have 2 copies of this single tensor, and I'm contracting the 2, like I'm combining the 2 physical bases, and basically these virtual ones have to be either you have a 0 and then you have a 0, you have a 1, you have a 1. And you can think of these as kind of classical labels. And so this tensor, if you write it out, is like if these 2 are equal, either you have 2 identities or you have 2 times z, which is also identity. So this is delta AB identity, and then you have a sigma z if they are different. So this is some sort of argument. And you can also write it as over AB of sigma z A plus B. The A here and the B here. So this is the pepo without the weights, and now if you want to put the weights, For example, you can split it up into like 8 pieces and add a little bit on each side, so everything is nice and balanced. So you can put the weights back here. Each of these is 1/8 of the tangent, hyperbolic tangent, and so you just have to basically add the corresponding weight here. But it's not, it just changes these numbers to something which depends on it. Doesn't really change. And so just to kind of try to argue quickly what happens, in order to compute this boundary state, I need to take 2 copies of this and contract the physical, right? So what I need to do is take 2 copies.
Is that just a pepo for rho v you get in the end? You take the copies.
So this would be A prime, B prime, and then I want to do a trace. This is what Hilbert-Schmidt's color product of this pepo would be. And just use the formula, and this is a bit of a game of graphical calculation and kind of keeping track of indices. You get here that this is the trace of sigma z power a plus a prime plus b plus b prime. Because every time you have a 1 here, it's a sigma z is appearing, and then you have times these 2. And so you see that that number is 0 unless that some the exponent vanishes. And so this, there are 2 reasons for which this can vanish. One is that A and A prime are 0 and B and B prime are 0. Or because they are both equal to 1. So you have these 2 cases. And my claim now is that both of these 2 cases are tensor product between the left side and the right side. And so you can see this because you can write out all these conditions on A and A prime and B and B prime, but there is no cross condition. So the condition on A you can collect, and so this is somehow the tensor product of having 2 zeros or plus 2 ones. Tensor with itself. That's telling me that the tensor. And this one is the same but with the opposite. And so let me call this like identity with a hat, and let me call this X with a hat, because they kind of look like a little bit expanded identity and expanded X matrix. So we'll be, can I have like a minute to what happens is that now if we start contracting this tensor on a bigger region, this part and this part will give you a 0 when you multiply together. So we do not mix. And so this is how this product approximation appears. Because you get this big region. In each, you put this thing and you start contracting. And so along the plaquettes, these circles form again with the weights. And then you have these uncontracted ones at the boundaries. Now what happens is, because this identity hat and this X hat, when you multiply them, you get 0. If one of these is the identity, then the corresponding one has to be, and this basically forces everything else to be identity. So this kind of gives you an expansion of a lot of identities plus an expansion with a lot of these. And you put the weights and you compute the weights, and you realize this term is the dominant one. So this is how we get our sigma. You actually perform this calculation, and you get that the term is exponentially bigger than this one. So you can just keep this, drop this, get a product sigma, and approximate your boundary state.
And this works fine in temperature.
Huh?
Works fine in temperature.
And it works fine in temperature. The constants will depend on beta. We will have like an hyperbolic tangent appearing, but it's smaller than 1, and so as soon as beta is finite, this term will go to 0 exponentially fast. Sorry for going a bit over time.
Okay, thank you.